you have a lot of rules for derivatives that you have memorized and know now. So we're going to use these rules in a variety of applications. The first we're going to look at is rate of change. Now, we've spent a lot of time talking about rate of change earlier and found out that a derivative is a rate of change. But these problems are going to expand on what we did before. So first we'll look at a couple of problems about rates of change. Then we'll look at some other types of examples also of derivatives. So let's look at this first example. The problem that we have to deal with now has to do with laptop computers. We're given that the profit in terms of the quantity of computers is negative 100,000 plus 4,700 Q minus 0.26 Q squared. So that's the profit in terms of the quantity of computers. However, the quantity of computers is in terms of N, which is the number of employees at the firm. So the quantity that is produced depends on the number of employees. According to the formula, 28N plus 0.01 N squared. And we're asked to find how fast our profit is changing when there are 50 employees. So when it says how fast is something changing, that's a rate of change, that's a derivative. So we're looking to find the derivative rate of change for n equal to 50. So we want the derivative p prime in terms of the number of employees, except p is in terms of q, but then q is in terms of n. So we can go back to the time that we did the rates of change to take the derivative, where we have an intermediate variable. So q here is our intermediate variable. So it's a derivative, in this case, with the intermediate variable q. So let's try to think how we did that. If I take the derivative of p with respect to n, another way to write that is the derivative of p with respect to n. But we have to go through q, so we write this first. That's the same as the derivative of p with respect to q multiplied by the derivative of q with respect to n. So let's take derivatives. The derivative of p, the derivative of this piece right here, derivative of negative 100,000 is 0, it's constant, plus the derivative of 4,700q is 4,700, minus the derivative of 0.26q squared, 2 comes around front and multiplies by 0.26, makes that 0.52q, and that is the derivative of p with respect to q. So let's multiply now by the derivative of q with respect to n. Derivative of q would be 28, derivative of n is 1, plus the derivative with the n squared, 2 comes around front, makes that 0.02 n. So I've taken the derivative, and I need to know what this is when n is equal to 50. So I have an n here, so I could figure out 28 plus 0.02 times 50. But here, I don't have n, I have q. But I have a relationship between n and q. So let's go back up to here and find out what q is when n is 50. I plug it in, 28n is 28 times 50 plus 0.01 times 50 squared, and that number turns out to be 1425. So when there are 50 employees, they can produce 1,425 laptop computers. So that's the number that I have to now put down here in place of q. That's where 1425 goes. So we plug that in. 4,700 minus 0.52 times 1425. Oops, another parenthesis. Multiply, subtract, multiply and add over here, and I end up with 114,811. That's what P prime is of 50. I have 50 employees, then my change in profit. My profit is increasing $114,811 when employees number 50 and when I say profit is increasing that amount when employees number 50, that would mean for an additional employee. Or you could say it's increasing that much per employee when there are 50 employees already there. That seems like an awful big jump for one more employee. Must really get everybody all cranked up to make some more laptop computers. You've seen the t-shirt problem, and you want to do like I did, is to take out and rewrite the parts that you need to use the worked problem. When it's a big paragraph, sometimes it's difficult to keep track. We were told that the cost is $15 for one shirt, and that cost is decreasing 10 cents per month. The production quantity is now 100 shirts, which is increasing 2 shirts per month. And the question asked us, how fast is cost changing? Changing is the rate of change, so that means we have to use a derivative. And it talks about cost, so we're interested in a total cost function. We don't actually have to create a cost function like you may think. Let's define the variables that we have to go with some of these numbers. So cost, let's let C equal the total cost, and that would be to produce all the t-shirts. Let S equal the shirt's cost, and that's for one shirt. And then we'll let N equal the number of shirts. Total cost is the cost for one shirt times the number of shirts. Cost for one shirt S times the number of shirts. Now, this is our function. I want to find how fast it's changing, so I need a derivative. Now, let's just take the derivative here. If I have cost is S times N, the derivative C prime, if this is times its product rule, would be first S times derivative of the second plus the second N times derivative of the first. That's S prime. Well, let's go back and see what information we have to go with this. I have all these numbers. S is the cost for one shirt, which is $15. So for S, I know that that is $15. N, the number of shirts, is $100. N is 100. N is not dollars, it is the number of shirts. 100 shirts. I need something for N prime and something for S prime, but that's where those increasing and decreasing words come in. If cost is decreasing 10 cents a month, that is the rate of change of the cost of one shirt, which would be S prime. And it says it is decreasing 10 cents we'll use the decimal since 15 is in dollars. Negative 0.10 means it is decreasing 10 cents a month. N, the number of shirts, it said N is increasing 2 shirts a month. N is equal to 2. I've already got the numbers in. What I have found right here now is C prime at those particular points. When cost is $15 for 1 shirt and the quantity is 100 shirts, and I know increasing and decreasing. So if I multiply 15 times 2, 100 times negative 0.10, which means I'll be subtracting, I end up with C prime is 20. So that tells me that the cost is increasing $20 per month. And that will be at these particular values when I know how much each shirt costs, value for S, and I know the number of shirts that are produced, that N is equal to 100, and what their individual rates of change are. I didn't need to create a function. I just needed to create a function in terms of letters that I can then substitute in my numbers. The problem told us that the percentage of households with VCRs followed this formula where T was the number of years since 1980. So if you put in T equal to 0, that would give you an idea of how many approximately households, well, the percentage of households that had VCRs back in 1980, before you were born probably, way before you were born. The question we asked was, how fast is it changing? How fast was it changing in the year 2000? If it's something is changing, it's a rate of change, we have to take the derivative. Now this is a fraction, and we have a quotient rule. The quotient rule usually intends for there to be a variable in the numerator and a variable in the denominator, but we only have T in the denominator. However, for this particular problem with all these big numbers, we're going to use the quotient rule to take the derivative anyway. So let's find P prime of T. Quotient rule says if you have a function f over a function g, quotient rule says to take g times f prime minus f times g prime over g squared. So that's what we're going to do. We start with the denominator, g, multiply times derivative of the numerator. But remember I said the numerator doesn't have a variable in it. So if it doesn't have a variable, the numerator derivative is 0. So the first part of the quotient rule, bottom times derivative of the top, is 0. Then it's minus top times derivative of the bottom. So it is 72.5 times the derivative of the denominator. 1, derivative is 0, plus 75.473 is a constant multiplied by that. So I have the constant multiplier times e to that power, but that's really going to give us a lot of long stuff. Let's back this over a little bit. Bottom times derivative of the top. Bottom times 0 is 0. Minus top times derivative of the denominator. Derivative of the denominator is 0 plus 75 plus 473 times the derivative of the e, which is e to the negative 0.6486t times derivative of the exponent. Derivative of the exponent is just the decimal part. Negative 0.6486. And then all of that over the denominator squared. That's a lot of numbers in there, isn't it? Well, when you do modeling, you don't always get nice numbers. You do get real life data, gives you real life interesting numbers. Squared. Denominator squared. What a combination of numbers. But we don't have to do a lot of simplifying if you don't want to. We could multiply negative 72.5, which is a constant, times that constant, times that constant. We have a negative sign, and a negative sign makes it a positive 3,549 times our E term over that denominator again. 86T squared. That's the derivative. I used the quotient rule, bottom times derivative of the top. I got 0 minus top. And the derivative of the bottom, I have the constant multiplier times e to the power times the derivative of the exponent because of the chain rule. Multiplied together, and I simplified. And we want to know the rate of change in the year 2000. I have found the rate of change for every year. And since 1980, 2000 would be 20. So I take p prime of 20. So for this t, I'd plug in 20, multiply times the exponent, then find what e to that power is. And that's something you might want to write down because it's in here twice. I have this piece, e to that power, and I have it again down here. So keep track of things like that so you don't have to keep doing the same calculations over and over again. Get your numbers, put them in, and we end up with a very tiny decimal. This is the percentage, that's the change in the percentage of households that have VCRs per year. So this says that 0.00825% of households was the only time that the number was changing after 20 years in the year 2000, which makes sense because DVD players started coming in and taking over for VCRs. So this is a very small percentage change increase per year. We're going to look at an example with marginal analysis. Now, remember that marginal is a rate of change with respect to quantity of a revenue function, a cost function, a profit function, a demand function, an average cost function, several different functions in business. But the key is that it has to be a rate of change with respect to quantity. So let's look at the example we're going to do and see if there's anything we have to work specially with this problem. The problem you saw is a problem with membership in a health club. And we're told that there are currently 20 members. And so the quantity is now 20 members. And we want to know how fast the profit will change if they add 3 new members. So currently 20 members, we want to add 3 more. And we want to find out how profit will change. So we need a profit equation. Profit is revenue minus cost. Revenue is price times quantity. Cost is fixed cost plus variable cost. So we need to try to put all this together in a profit equation, and then we'll find the rate of change of the profit with respect to quantity. We have one big problem, though. We're given that the demand function is the function Q of P equal to negative 0.05P plus 60. P is the variable. P can't be the variable. We have to have quantity Q as the variable. But that's okay. We'll just solve for P and find out how we have this equation with Q as the variable. So let's subtract 60. We want to isolate P. And then we'll divide by negative 0.05. And that'll tell us what P is equal to. I'll split this up and go Q divided by negative 0.05, and that will give me negative 20Q. Negative 60 over negative 0.05 gives me a positive 1200. So now I have the function price in terms of quantity. So Q is the variable, and that's what we have to work with to do a marginal analysis of a problem. So let's come back up to our revenue equation up here. And when I want to do price times quantity to find revenue, this is my price equation. So this will equal negative 20Q plus 1200 and then times the quantity Q. So all of that is revenue. I subtract cost, and we were told in the question that cost is $4,000 and $52 per member beyond that. That exactly is $4,000 for fixed cost plus $52 per member, that's the variable cost, so that has to be multiplied by a variable, which is the quantity, the number of members. So this will give us our revenue minus cost, which is profit. If you multiply through by the revenue, we have negative 20Q squared plus 1200Q, then minus 4,000, and minus again, we have to subtract every cost. So we put these together, we'll have negative 20Q squared plus 1200Q minus 52Q will be a plus 1148Q and then minus 4,000. So that this is our quadratic profit function. Now that I have a profit function, I can find the rate of change with respect to quantity. So I'll call that capital P prime of quantity, negative 40Q plus 1148. And I want to know the change at 20 members. P prime at 20, I put my number in, negative 40Q. I can also call that marginal profit at 20. And I end up with 348. 20 times negative 40 and then add 1148 gives me 348. That's for one additional member. Marginal profit, remember the marginal means one additional member, one additional unit of our quantity. But I want to get 3 new members. I want to find out how profit is changing if I get 3 new members. Well, since this is positive, I'll multiply that by 3, and I'll find out that for 3 new members, profit will increase by 3 times 348. So that would be $1,044. That would be the profit if they can take 3 new members into their health club. This application of derivatives is about elasticity of demand. We're given a demand function and we want to find the elasticity at Q equal to 50. We've had formulas for elasticity before, but we had 2 separate formulas. For one, we found that elasticity was equal to P over Q times Q prime. And the other version of it was eta equals P over Q times 1 over P prime. Well, if I take the derivative of my demand equation, since this is P, I'll get P prime. So this is the rule that we will use. So let's see what we get if we use P over Q times 1 over P prime. I need P prime. I need the derivative. Now you have rules for derivatives, so you don't have to do a shortcut method and use it numerically to begin with. We can simply take a derivative. So let's just get started. P is all of this. So elasticity is equal to P, 100e to the negative Q over 10, that's my exponent, over Q, and for now I'm not going to put in 50, I'm just going to put in Q, times 1 over P prime. I have to take the derivative of P. Well, 100 is the multiplier. Write that down. The derivative of the exponential part is e to the u, e to the negative q over 10, times the derivative of the exponent. Now, if you're going to take the derivative of negative q over 10, the 10 in the bottom is a constant. You don't need to use quotient rule. You can think of that as the same as negative 1/10 times q. That's exactly what this means. So the derivative is negative 1/10. Now the reason I didn't jump right in to put in q equal to 50 is because I did not want to put in q equal to 50 here and here and here, because notice that this is two fractions multiplied, all one big piece. There's 100 on top and 100 on the bottom. They cancel. There is this exact same e term on top and the bottom. They cancel. I don't have to put 50 into the e exponential part at all. What I have here now, elasticity is equal to 1 over q times 1 over negative, let me get enough in here, 1/10. That looks like it's in the bottom. 1 over negative 1/10. 1 over q would be 1 over 50 times 1 over negative 1/10 inverts times negative 10. That's negative 1/5. Much nicer than when you had to do it in the past with plugging in a lot of numbers to find what P prime was equal to. So my elasticity equals negative 1/5. Absolute value of that would be the absolute value of negative 1/5, which would be 1/5, which is less than 1, makes this elasticity inelastic. Absolute value is less than 1. You could also write it as a decimal if you want to. That's fine. But do pay attention and use the formulas first before you start trying to plug numbers in. It can make your work much nicer.